To get a sense of TensorFlow syntax, we're going to be looking at an example that you already know, which is simple regression, which you've done lots of time already. And the regression example is going to be based on a TensorFlow presentation at SciPy in 2019. But before we get to the regression, let's first get an idea of what the math looks like when you use TensorFlow. So the first step is that we can define TensorFlow variables. So I'm going to have two variables, z1, z2, using TensorFlow, and then variable, and we'll give it starting value 1.0, and we're going to do exactly the same for z2. We're going to define a loss function, which here is going to be a very simple one. Later on it's going to be based on a regression. So the loss function is going to be called myLoss, and it's going to be equal to c1 minus a squared plus c2 minus b squared. So the advantage of this loss function is that it has pretty obvious properties. So first of all, it's convex. Yeah, it tends to infinity as z1 or z2 gets bigger and bigger. And the second thing to observe is that the minimum of the function myLoss is going to be achieved when z1 is equal to a and z2 is equal to b. Yeah, because this loss function is positive because it's squared. We're not looking at complex numbers. So the lowest it can get is 0, and I can actually achieve 0 by choosing z1 equal to a and z2 equal to b. The other thing to observe is that this function, myLoss, is actually not a function of the TensorFlow variables z1 and z2. Yeah, because TensorFlow already knows that these are variables, so I don't need to declare them here in my function statement. So now things that I can do is, for instance, I can look at the, with TensorFlow, I can look at the derivatives of this function, myLoss. So the way to do this is to define context, so don't worry about the syntax here. It's no problem if you don't quite understand what's happening. So I'm going to be looking at myLoss, and I'm going to specify that a and b are both equal to 0. Yeah, so remember the parameters of myLoss are a and b, not z1 and z2. So this is going to be the value. And then tape, so that's the thing I've defined here. So with the gradient tape as tape, so tape dot gradient of value, and I'm interested in the derivatives with respect to z1 and z2. So I can run this code. So the output is not so nice because these are TensorFlow variables, but you can see that this derivative is equal to 2.0, both in the direction of z1 and in the direction of z2. Yeah, so if you take the derivative yourself, you get 2 times z1 minus a, and a is actually equal to 0. And the starting value of z1 is equal to 1. So I get 2 times, for the derivative, I get 2 times 1 minus 0, which is indeed 2. And this is the case both for the derivative with respect to z1 and the derivative with respect to z2. Another operation that we need is the following. Assign sub 1.0. Yeah, so what it does is it takes the value or the current value of z1, which in this case is 1, and it subtracts the value 1 of that. Yeah, so my new value is going to be 0. Yeah, so if I run this again, I'm going to get minus 1 because the previous value was 0, and I subtracted 1, so I get minus 1. Yeah, so simply play around with this code. You know, you have the other function is called assign add. So if I add 5, I get 4 here. And if I do it again, I get 9. Yeah? So now we can program our own minimizer, which is going to minimize the function myLoss. So as before, there's going to be a learning rate. So let's choose it equal to 0.05. I'm going to define number of steps equal to 100. Oops, 100 will be enough. So then we do for I in range of steps. We're going to do the following with Tensorflow gradient tape as tape. Loss is going to be myLoss 4, so A is 4 and B is 4. So that means I actually know where the minimum of this function is. It's going to be at z1 equals z2 equals 4. Now let's see whether, oops, wrong T. So let's see whether this function is going to be able to figure that out. So gradients is going to be equal to tape. So gradient loss C1 C2, and we're going to do Z1 sine sub gradients 0, because it's derivative with respect to Z1, so that's the first element in gradient, so that gets index 0 times eta. I'm going to explain this equation in a second, so don't worry. And the same for C2, Z2 assign sub gradients, now we need the second element, times eta. To get a bit of a sense of what's happening, if so every 20 steps we get some report of what's happening, print step percent D loss percent F. Yeah, so the percentage signs are placeholders. So the first one is going to be replaced by I, which is the index running over the steps. And the second is going to be replaced by loss. We're going to use the NumPy method to make it a bit more readable. So that's this one, that's that one. And then finally what I want to see is what's the value for C1 and what is the value for Z2. Oops. Let's see whether I didn't make any errors. No, doesn't seem so. So we started a big loss of 34. Then it comes down rapidly, and in step 80 the loss was already pretty close to 0. And indeed what it finds is that Z1 and Z2 should basically be 0 to minimize this function. Yeah, which is correct because A and B are 4 and 4 in this case, and therefore the function myLoss is minimized when Z1 is equal to 4 and Z2 is equal to 4 as well. So why do we have this sort of updating function here? So again, let's write this in LaTeX to make it a bit more readable. So we have C1 is equal to Z1, yeah, because assign sub is basically the same as minus equal. So we subtract from this our learning rate eta times d, and let's call the function simply f to make it a bit more readable, and we take the derivative of f respect to z1. So this is what our update rule looks like. Now the intuition for that updating rule is the following. So plt plot, so let's numpy arrange, let's say from -1 to 1.1 with steps of 0.1. And we're going to take that same thing and then look at it squared. Yeah, so it's a simple convex function. The x label in this case is C1 and the y label in this case is f. So the function looks like this. Now if I want to minimize this function, and let's say I'm somewhere over here, that means that the derivative is positive. So if I want to get to the minimum, what I have to do is I have to walk to the left. I should reduce z1. So if you look at this equation, that's exactly what happens. The new value of z1 is the old value of c1 minus eta, which is our learning rate, times the derivative. So if this derivative is positive, I walk to the left. I'm going to reduce z1. If I'm over here, the derivative is negative. And if I want to get to the minimum, I should walk to the right. That's exactly what this equation does. It takes the old value minus this derivative. So I get a positive value here. So I get something positive times eta. So z1 is increased if I use this equation, which is correct because I need to walk to the right to get to the lower values of the function f.